Okay, so the multiple choice questions, the zero latitude, those are the ones that have, zero latitude is the equator. You can go north and south of that lines of latitude. The second one, the longest day of the year in the northern hemisphere would be in the summer solstice or at the summer solstice. Later on in this test, you guys told me that's about June 21st-ish. Los Angeles is in the Pacific time zone. B is the best answer for number 3. Number 4, latitude is the angular measurement in degrees. If the whole angular measurement kind of thing threw you off, latitude is north and south of the equator. So C is the best answer for 4. Number 5, actually, this is one of the reasons I have a little arrow there. And I spotted you guys 5 points. So instead of taking it out of 80, I took it out of 75. I think this is a tough one. Basically, kind of centered around the, let's see. Centered around the winter solstice is when actually, if you were north of the Mason-Dixon line, no. If you are north of the Arctic Circle, you are going to have a lot of darkness. So the best answer there actually is the vernal equinox. So starting at the vernal equinox.
Can I leave?
No, I don't have makeup exams, but what we'll do if you ever miss a test like this is we substitute your final in for that. So,
Oh, okay.
So you're fine. Only leave if you want to leave. So actually, vernal equinox is the right answer there. Anyway, number 6. The number of hours of daylight on Earth depends both upon the time of the year and your latitude. So the best answer there is C. And then moving on, if I can do it here. Okay, the next one. The plane of the Earth's equator is tilted 23.5 degrees relative to the plane of the Earth's orbit about the sun. That's related to its axis is tilted, so hopefully you recognize the 23.5 degrees tilt. Question number 8, Kepler's first law states that the planets orbit the sun in a shape called an ellipse, so B is the best answer there. Question 9, the name given to a planet when it is closest to the sun, we call that perihelion, so that's C. Question number 10, the planet whose axis of rotation lies in the plane of the ecliptic, the best answer there is B, Uranus. Question 11, the planet with the great red spot is Jupiter, A. Question 12, the planet with the most predominant rings is Saturn, B, although all of the Jovian planets have rings. Question 13, the planet with the largest volcano in the solar system is Mars. That's that Valles Marineris. On to the next page. Question 14, which of these is not a dwarf planet? Mercury is a full-fledged planet. Ceres is a dwarf planet in the asteroid belt. Pluto and Eris actually are what we call trans-Neptunian objects. Okay, they are dwarf planets out there. Question 15, the planet that most resembles the Earth's moon is actually Mercury. So D is the best answer there. The next question actually is a question about a moon. I'll just give you this one.
Okay.
The moon Charon actually is one of Pluto's moons, so it has 5 moons. It's one of the 5. So E is the best answer for 16. Question 17, when a meteoroid enters the Earth's atmosphere, that's actually the event we call a meteor, okay, or a shooting star. So A is the best answer for 17. Question 18, with regard to comets, the thing that surrounds the nucleus is called the coma, or the head of the comet. Question 19, comets are composed of, I've been saying rock and ice, so this says dust and ice, but the best answer there is still A. That's what comets are composed of. Question 20, as a comet approaches the sun, it begins to vaporize. So because of that, actually the coma and the tail increase as it gets closer to the sun. Question 21, the moon completes one orbit about the Earth every about 28 days, 29.5 days about every month. A is the best answer for 21. 22, the moon always presents the same face to us. We call that the near side of the moon because actually it rotates on its axis the same rate that it takes to complete one orbit about the Earth. Question 20, so the best answer there is B. Question 23, the solar eclipse can only occur during a new moon phase, so C is the best answer there. Tides, 24, are caused by A, the gravitational pull of the moon and the sun. 25, spring tides occur. Those are especially high tides that occur when the sun is also on the same side of the earth as the moon. So that would be the full and new moon phases. So B is the best answer there. Question 26, the asteroid belt, of course, is between Mars and Jupiter. B is the best answer there. 27, we call the visible surface of the sun the photosphere. Okay, so the best answer there is A for 27. On to the next page. Question 28, the surface temperature of the sun is about 6,000 Kelvin, D. Question 29, the number of A, sunspots vary on the sun over an 11-year cycle. Question 29, the condition where basically the inward force of gravity and the outward pressure that's created by our sun are balanced, we call that hydrostatic equilibrium, A. Question 31, of these spectral types, which one is the hottest? That would be A, the O-type star. Question 32, if we plot the absolute magnitude or brightness of a star versus their surface temperatures, we have created A, Hertzsprung or HR diagram. Question 33, the greater the mass of the star, the faster it lives its life. So A is the best answer for 33. 34, when the sun moves off the main sequence, its next step is A, red giant. Question 35, the remaining core of a planetary nebula is called a white dwarf, A. Question 36, an incredibly dense object, I know I misspelled dense, such that light cannot escape from its surface is called a B, a black hole. Question 37, pulsars are created by the presence of A neutron star. Question 38, our home galaxy is C, the Milky Way galaxy. Question 39, the sun's energy is generated from the fusion of, the best answer there is C, hydrogen to form helium. Question 40, 12 hours of daytime and 12 hours of nighttime occur during the C, the vernal and the autumnal equinoxes. Question 41, the color of a star reveals D, its surface temperature. Next page, question 42, when we say how bright a star is, it's based upon this scale where just kind of dark skies, the dimmest star that you can see is actually magnitude +6. So B is the best answer there. 43, if a star is hot, it's going to appear D, blue. Question 44, the diameter of the Milky Way is about 100,000 light years, side to side. Question 45, the Andromeda galaxy is a spiral galaxy, so A is the best answer there. So those are each worth 1 point apiece, and then these next part were each worth 2 points apiece. So I was after prime meridian. I think if you put meridian, I took it too. But prime meridian is the thing that basically starts the lines of longitude. It goes through Greenwich, okay, and then it actually, the other side of it is the international date line. Question 47, precession is basically the kind of rotation of the Earth's axis, about 26,000 years. 48, the name given to when a planet is farthest from the sun is aphelion, so that's opposite of perihelion. So in some cases where if you had like a related term, if you put perihelion, I gave you 1 out of 2, that sort of thing. For 49, if you put nebula, I think I gave you 1 out of 2, but I was really after solar nebula is basically the thing that started out as kind of the gas that our solar system came from. Question 50, I was after meteor shower. If you simply put meteor, I think I gave you 1 out of 2. But a meteor shower is when the Earth is passing through a debris field that was probably left by a comet. The last page, a few more vocabulary. When a space rock makes it through Earth's atmosphere and you can pick it up, that's called a meteorite. Mare are the dark regions on the moon, and highlands are the light regions. Question number 50, the plane that contains the Earth and the other planets is called the ecliptic, or the plane of the ecliptic, or the ecliptic plane. Question 54, the celestial sphere is kind of that sphere that basically it's a model. we can put the stars on there and put the Earth in the center, and kind of, it's not how it works. But question 55, the surface of a black hole is called the event horizon. So then the last one's a short answer. They're kind of worth an assortment of points. So for 4 points, I wanted you to give me the equinoxes and the solstices. Pretty good there. The next one for 3 points, I wanted you to list the planets in order and then group them. So it's funny because as I was grading your homework, some of you guys actually did what I did on my answer key. You put the sun there. I was like, oh, that is so cute. Of course, we have our interterrestrial planets and our outer gaseous or Jovian planets. And then the next one, I wanted you to sketch, it's worth 4 points, so kind of like 2 points each, the eclipses, how they occur. So the first one I drew is the solar eclipse, where the moon is blocking out the disk of the sun. This happens at new moon, right? And then the other one is the lunar eclipse, where this happened at full moon, where basically the moon passes into the Earth's shadow. Some outstanding drawings here. Oh my gosh, I just like, wow, that is so cool. And this last one, and I didn't realize it till the end, this is a new test for me, and so I got these figures by basically off the internet, kind of copying, pasting 8 times. So I ended up in my Dropbox, kind of a long story because the iPad does better than the PC. So they were in my Dropbox, I had to copy, and anyway. So I ended up with 2 that are actually the same, DRAT, number 4 and 6, was not my intent. But you all did pretty good. And I also figure that I spotted you 5 points, I took it out of 75 instead of 80, and if you just missed a few here or there, you got full credit, so that was worth 4 points. So not bad, pretty good. Okay, so again, your final exam in here, you're going to see a lot of these same questions again. Okay, just today I have, because I think I meant to do it before. Let's see if this will go here. Just today I posted these under, you know where you guys go to see your grades and such? Oh, I've been looking at eyepieces. So if we go out to the course, now under doc sharing, you're going to see a folder called unit exams. And now there are all 3 unit exams out there, the answer keys. It's been kind of fun for me because I feel like we dabbled in physics, and then we dabbled in chemistry, and then we dabbled in astronomy, and next we're going to dabble in meteorology. So hold on. So I don't think I don't have the patience to, but let me know if you can't find it. It is out there finally just today. Okay? All right. So speaking of dabbling in meteorology, here we go. So the hydrological cycle, I have this on a slide coming up. The hydrological cycle is the water cycle, i.e., this is the water cycle. Okay, and you guys know the water cycle. You guys care about the water cycle. Bless you. Okay, if this is like my land, okay, the water cycle, obviously, I don't know where you want to start, but we're going to talk about clouds. Okay, if that's my cloud, okay, from my cloud, if it becomes full enough, okay, actually you can have precipitation, okay, and then we can have the sun dry up the rain, or at least some of it, okay, and then it can condense again to a cloud and it can rain again. That's the water cycle, okay? So we'll talk a few more details than that. But the thing about the water cycle, actually, is we need to focus on water. Our planet is unique. Our planet is like the only planet that can have, on an ongoing basis, water. Okay, other planets have water because it is most likely deposited from comets. That's how we got our water. But they're not in the 3 physical phases. We have liquid water, okay? We have ice, solid water, and actually, and we're going to do a lab, I know for sure, that we're going to take a room, probably the chem lab, and we're going to see what's the humidity in the room. Okay, so, and actually, if you have naturally curly hair, you can already tell what the humidity is in the room. There are actually like devices that use hair, usually horsehair, but can use people hair, that kind of, it crinkles up and kind of expands, and it tells you what the humidity is. So my point is that there's invisible water vapor everywhere. Okay, so water in its 3 phases associated with the Earth. That's pretty darn cool. So you may or may not know, but actually the Earth's surface is mostly covered with large bodies of water. So here's a photograph. We get some neat photos of the Earth these days, because we have the International Space Station sends us back some great images, but a lot of water. So I've heard 3/4. This says 70%. I've heard 75%. Basically, if you look at a globe, it's mostly blue. Actually, there's been movies made about that. Waterworld, that sort of thing. Actually, I don't know how much we'll end up talking about it, but that's one of the things we're concerned about, is that we don't want any more water. Okay? And there's a slide coming up that says actually a lot of Earth's water is tied up in its solid phase, at the poles, in glaciers. And as that melts, we get more water. We don't want more water. Okay? Yeah, so a lot of the water is actually tied up not in oceans, okay, but actually in glaciers. So I mentioned that we've got water vapor in the air. So I'm hoping that you guys are okay when I say water vapor. I'm hoping you already kind of connect it with water gas, water vapor and water gas. Okay. So sometimes the air is dry and sometimes the air is not so dry. Okay. If you're like, well, on hot summer days, the humidity is almost what gets us, So move to Arizona, it's a dry heat. So here's where the water is. All of the water in the Earth's atmosphere, whether water is liquid in the oceans or whether the water is solid in glaciers or whether the water is vapor or gas, all of the water we call the hydrosphere. Hydrosphere. You might be like, oh, I heard of sphere before. I've heard of the atmosphere. And actually, that's that. I think when we talked about Earth, we said some planets have an atmosphere. That's the gases. The hydrosphere is the water associated with the planets. So most of it, our water is 97.2% is in our oceans. You're like, dude, really? Okay, so about 3% is not in our oceans. Where is that 3%? And this is a pie graph to show of that 2.8%, how much of it is tied up is solid at the poles and glaciers. Okay, not all at the poles, but kind of near the poles. So that's a lot. So you'd be like, well, when you go to take a shower or when you go to, where did that water come from? Well, it had to have come from this little sliver. And so what's that little sliver? Well, we have groundwater. So it's not the sliver, but a large part still of that 2.8% is not accessible. It's under the ground. And actually, that's been in the news off and on as we talk about maybe tapping into our resources that are underground. We better be careful what we're doing with our groundwater. So that little tiny sliver is basically what we have to use in our day-to-day lives. Okay? That's not much. So as we talk about the hydrological cycle is the water cycle, right? We need to kind of get a fix on this whole, the three physical phases that water can be in. Okay, water can either be a liquid, water can be a gas, or water can be a solid on Earth. Okay, so how does that fit in with the whole precipitation or water or hydrological cycle? Okay, well, we need to kind of explore that a little closer. So, one of the things about matter, and actually this is where I kind of like this exploring physical science, because we did talk about that all matters in motion, I think. Okay, all matters in motion. So one of the things about it is if I were to, if this is my matter that's in motion, if I were to zap some of its energy, if I were to cool down, guess what? It would go slower. Okay, if I were to cool it down more, it would go even slower. Okay, one of the things we talked about in energy, one of the things we talked about in physics is that actually we can say how much kinetic energy that matter has by taking its speed, its velocity, and it's actually kinetic energy is 1/2 mv squared. So we can, the faster the velocity, the more kinetic energy it has, basically. So the three physical phases of matter, let's take a look at those with regard to kinetic energy. And I have a video, we'll see if it plays for us. I might have played this before, but remember all matter has a motion. in this universe anyway. Maybe. Okay. It's kind of nice because now we're just focusing on water. That's all I care about, water. So I mentioned that when we looked at a solid here a minute ago, I said that actually those in water that's in an ice cube, they're stuck together really. Okay, they're really very much stuck together. What sticks water molecules together actually is a special type of bonding called hydrogen bonding. And I know that Shipman actually, back in the chemistry unit, I think talks about hydrogen bonding. But not all substances have hydrogen bonding. Okay, so that's what connects water molecules together. And actually, I have a little bit to kind of say what hydrogen bonding is. Remember before we did astronomy, we dabbled in chemistry. And I may have even used this as an example. But we talked about, I'm going to draw a water molecule down here. Okay, H2O. So we actually have a hydrogen in the middle, and then we have, hydrogen in the middle. I meant to say oxygen. We have an oxygen in the middle, and then two hydrogens coming up, and it's kind of bent like that. That's like what a water molecule looks like. And what this slide is saying is that when it comes, and you guys did remember you guys did the electronegativity? So the electronegativity difference, okay, is basically you take the electronegativity of your hydrogen atom and you subtract the electronegativity of your oxygen atom, and it's the absolute value of. But my point is that the electronegativity of the oxygen is pretty high, so it runs around, actually is partially negative, and both the hydrogens run around as partially positive. So that when this water molecule wants to form an ice cube and join with another water molecule, this is what it looks like. So I'm going to draw another water molecule down here. I think I'll draw it this way, so I might make it easier. Here's my two hydrogens, okay, partially positive. Oops. Oxygen's partially negative. The two hydrogens are partially positive. And then this dot, 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 that actually is my hydrogen bond. And between two water molecules, actually, you can have multiple hydrogen bonding. Okay, so that red right there are my hydrogen bonds. That's all this is talking about. So like you saw a minute ago with the kind of solid liquid gas, okay, as a solid, all sorts of hydrogen bonding or all sorts of intermolecular bonding. If it's if it's not water, it's other sort of bonding. Okay. As a gas, basically no bonds. So one of the things we need to kind of talk about, not necessarily wrestle, I guess, with right now, is when water goes from being ice, okay, to being a liquid, you probably say we can take an ice cube and we can heat it up. When you heat it up, what you're doing actually are breaking these hydrogen bonds. That's it. So here, kind of from left to right, I've shown ice, okay, and I've shown liquid water. If you compare the two in this liquid water, you finally see some free water molecules. In its ice state, it's very ordered. Okay? So that's it. So this adding heat is kind of hopefully intuitive. Intuitive means it makes sense. And I'm kind of counting on that. Okay? The water cycle that I showed a minute ago, what did the sun do? Okay, basically added heat to the liquid water, and what did the liquid water do? It vaporized to a gas. This is to say that I could add heat again, and what would I get? Gas, exactly. You got it. Exactly. Okay. So let's look at what we call physical phase changes. So if our three physical phases are solid, liquid, and gas, a physical phase change is when it's going somewhere between a solid, liquid, and a gas. Our physical phase changes. So you guys would tell me the whole melting thing means an ice or something's going from a solid to a liquid. That's cool. you guys would tell me that if something goes from a liquid to a gas, actually that's evaporation or vaporization. Evaporation, vaporization is the same thing. So we have what's called an energy diagram down here from your textbook. Okay, basically, one way to think about it is along the x-axis, okay, it says heat added. Basically, you're pumping heat into it, okay? So I'm going to add heat to this ice cube. So it kind of goes from left to right. I'm going to add heat to this ice cube. What's the ice cube going to do? It's going to melt, okay? Actually, you're probably going to see it form a liquid first, and then it's going to be entirely liquid. You know what I'm saying? This is kind of in between. So we're adding heat to it, and it does that. Okay. I'm going to add a little more heat to it. Okay, not room temperature, but actually I'm going to bump it up with a hot plate, and then your liquid is going to go to a gas or a vapor. That's all it's showing you. Okay, and we call this evaporation. That's it. Now, there is another thing, and there are definitely some good examples of this. Let's see. Where a solid breaks those bonds and goes straight from a solid to a gas. What would be a good example? Let's stick with water, obviously. So you guys probably don't remember this, but when we used to buy refrigerators, they didn't have an ice maker in them. Like, really? No ice maker? Oh my gosh. So you had to take plastic trays and fill them up with water and then put the plastic trays in your freezer. So the deal is if you did that, and then you came back like a day later and you got your ice, no problemo. But if you did that and you came back maybe 2 weeks later to try to get your ice, I don't know if you experienced this, but there's a good chance that basically what started, your liquid water solidified into an ice cube, and then you went back two weeks later and basically the ice cube shrank down to not much at all. What actually can happen and happens in our freezers, and I think it's kind of actually related to kind of getting our meat freezer burn, is ice can, what we say, sublime. It can go straight from a solid to a gas. Okay, it sublimes. I think sublimation, that's kind of the noun part of it, occurs when, like when we get a bunch of snow in the summertime, you know what I mean. We get a bunch of snow in the wintertime. We have a big old pile of snow, okay? And it's like, 10, 20 degrees Fahrenheit out. So it's really cold. That snow is not going to necessarily melt. But my thing is I really have seen snow piles go away even though it's really chilly. I didn't see it melt, but I see it go away. You're like, you're crazy, Mrs. Snipes. I'm like, no, I'm not. Sublimation, okay? So, you guys won't have to do any calculations, but we do know quite clearly how much energy it takes to go ahead and for something to go from a solid to a liquid. We know how much energy that takes. We know how much energy it takes to go from a liquid to a gas. We know how much energy we need to zap that material with in order to make that transition occur. That energy is called the latent heat, okay, latent heat. So if you're zapping something, having it change its physical phase, okay, that zap, that's your latent heat, okay? That's it. All right. Well, we need to talk about the opposite direction of phase change. We've been talking about what I call from left to right, kind of solid to liquid, liquid to gas, kind of left to right. We need to talk about the other things where actually a gas will go to form a liquid and a liquid will go to form a solid, okay? Starting out with kind of the gas going to form a liquid, a gas going to form a liquid, we call that condensation, okay? It happens, thank goodness. Now, the thing that's important here, actually, is as something goes from a gas to a liquid, okay, energy is released. I'm going to go ahead and do this. I'm going to go, let me do it this way. I'll put E for energy. Energy is released. You're like, really? I'm like, really? Here's the deal, and let's all start to think about this. I'm going to draw my cloud, and we'll talk about maybe why most clouds, if they're kind of undisturbed, have nice flat bottoms. So that's my cloud. That is my cloud. Anytime you see a cloud, basically what you are doing is you are seeing H2O I'm going to put a little L next to it. You're seeing water liquid. You're seeing water liquid. Anytime you see a cloud. Have you ever heard that like fog is basically a cloud at ground level? There is definitely something to that. What is fog? Fog is basically your little particles of liquid water. Liquid water, that's what fog is. And there is something to say for basically fog is basically a cloud at ground level. The thing about liquid water making a cloud milky white, or liquid water making it so you can't see in the fog, okay, is basically light. Light can pass right through a gas, okay? But light actually, when it hits liquid water, it does a sort of a dance. So you see kind of a, it reacts, it interacts, okay? So, let's see. So if a cloud is liquid water, guess what? It didn't start out as liquid water. It used to be a gas, H2O, G for gas. Okay, that got us our cloud. H2O gas condenses, form H2O liquid. One of the things about clouds is they tend to have this, I'll go ahead and say warm. They are warmed, I'll put it as they are warmed. Clouds are actually warmed by just the fact that water has gone from a gas to a liquid. Okay, why are they warmed? And I'll kind of draw your attention to this. That is why they are warmed. This E for energy, couldn't read my own writing there. Actually, that is latent heat. But latent heat that is released. One of the things I chose to talk about is hurricanes, because I think we should all know a little bit about hurricanes. But the hurricanes can be so humongous. A hurricane, it's a weather system. So one of the things about hurricanes is they have a lot of condensation, and actually that is the energy that fuels a hurricane. Okay, so energy is released as you go from right back to left again, the kind of the gas to a liquid, or the liquid to a solid. Energy is also released, and of course, something going from a liquid to a solid. We'll talk a little bit about snow in here because that's probably more near and dear to our hearts than hurricanes. Okay. So energy is released in that case too. And then kind of like sublimation is called deposition. I have a good example of this. Deposition is basically, it skips the liquid stage. So deposition, it goes from a gas right to a solid. So here's the deal. Frost is a good example of that. So the thing about frost is, it could be like, I don't know, like 25 degrees outside, 25 degrees Fahrenheit. And water freezes at 32 degrees Fahrenheit, right? So 25 is cooler than that. But what can happen over the course of the night is if you had water vapor, it's kind of humid out there, basically the conditions will be right for that water vapor to what we say deposit and go from a vapor right to a solid, frost. I love frost. It's beautiful. It's kind of, when it gets on your windshield, you can kind of see it looks like snow. It's got that crystalline look to it. So that's called deposition. And energy is released then, too. So actually, I have both physical phases here, or both types of physical phases. I'm hoping, you're kind of getting a handle on this. So let's see. Energy in. That's usually, that makes sense, right? Because, for instance, if we know we want to go from a solid to a liquid, okay, we're going to add energy. If we're going to go from a liquid to a gas, we know we're going to add energy, okay? We've talked about sublimation, right? But not so intuitive is the whole releasing energy. So we said that when condensation occurs, it releases energy. When freezing occurs, it releases energy. We said that actually with regard to frost, when water goes directly from a gas to a solid, it also releases energy. And those are all called latent heats. There's a number, there's a value. It's in units of joules, which are energy, right? So here's the picture of the hydrological cycle. Yay! I'll just put all these up here. Kind of a busy little slide. Nice little figure to put under your pillow. So it's stuff that you already know. That's kind of a nice thing. We know that water evaporates, And if it evaporates from the Earth's surface, you know, it's going from a liquid to a gas. We talked about humidity. Humidity is basically how much water vapor or gas is in the air. If the conditions are right, and we'll talk about what those conditions are, it can go ahead and form clouds. That is water going from a gas to a liquid, okay? Condensation. And if there is enough, let's see, if the conditions are right, basically the cloud will cry. If the conditions are right, basically the cloud will go ahead and drop its water. We call that rain or snow or hail or sleet. Okay, those are called precipitation. Now, I don't think I'm going to emphasize it much, but transpiration, if you're a biologist, you've probably heard of that term before. And I'm not a biologist. But transpiration actually is kind of it kind of sounds like respiration, transpiration, I don't know. It's a biological term. One of the things that plants do, they have these things called, I think, stoma, and they open up and they basically release water in its gaseous phase. So that's kind of a fun thing. Okay. So that's about how far I wanted to get, and we're going to pick up here on Monday.